All right, thank you so much. First of all, thanks a lot for the opportunity to present Fritz to you all. I'm really excited about this. So this whole project, let me just start off with this. So I'm Duev. I'm a research scientist at Caltech, and I'm involved with this project. And I'm really speaking on behalf of the Fritz Dev Team. And I just want to show you these wonderful faces. These are essentially the major contributors to the project. It's a joint Berkeley/Caltech initiative, but a whole bunch of other people also contributed. So we got Josh Bloom, Harry Krellenquick, Guy Neer, and Stefan van der Wald from Berkeley. We have myself, Matthew Graham, Ansi Kastlewald, and Kyung-Bin Shin from the Caltech side. Danny Galston started on the Caltech side. Now he's at LPL. He's an engineer there now. Michael Coughlin used to be a postdoc at Caltech. Now he's a professor in Minnesota. Leo Singer is at Goddard. He's a civil servant over there. So yeah, once again, thanks a lot for the opportunity to share this project with you. It's been a very positive experience for us all in the dev team. I'm sure they will agree with me on that, and I'm just very happy to share it with others. Really quickly, if for some reason you're not familiar with the Zwicky Transient Facility, I have one slide on it. So ZTF at a glance. ZTF is an optical time domain astronomy sky survey. We're at the 48-inch Schmidt telescope at Palomar, and in Southern California with a fairly large detector area, and we're capable of scanning the full night sky in one night. But we've been doing a 3-night cadence for the public survey in ZTF phase 1, and now we've just entered ZTF phase 2 on October 1st, and we'll be doing a 2-night cadence as a part of that survey. We're doing 3 filters: GRI, nominal exposure time of 30 seconds, and we go down to something like 20.5 in the R. At New Moon with a median image quality of 2 arcseconds. ZTF, as you know, was named after a prominent Caltech astronomer, Fritz Zwicky, and that's essentially where the name of this project comes from. That's just to remind you where the camera sits inside of the P48-inch tube. The main science drivers of ZTF, as you all I'm pretty sure you all know, but anyways, it's a fast and wide area time domain survey, and the main focuses have been the fast, young, and rare flux transients, then gravitation counterparts to GW sources, low Z type 1a supernovae for cosmology, then also variable star signs, eclipsing binaries, stuff like that, and also solar system objects. So I really like this image that's 2I Borisov from December 2018, so almost a year before it got discovered. So it's a pre-discovery image of 2I Borisov. A quick slide on the ZTF data processing flow to kind of show you where Fritz fits in. So really the central piece, so once the data is taken and transferred over to IPAC, the central piece of the pipeline is the real-time image subtraction and source extraction pipeline that produces the famous transient alerts, hundreds of thousands of those in any given night, up to 1 million, sometimes a couple million. And those get distributed to the world via Kafka streams. And this is essentially what we've been focusing on so far as part of Fritz. So those are stored somehow and then filtered and then marshaled, using those different pieces of software that have been developed over the years. And some of them were modern, some of them were kind of very old school and needed replacement. So this is essentially how Fritz was born, and I'm showing a schematic overview of Fritz as I understand it. So we have ZTF and friends as the discovery engines, and the task is to mine the data sets produced by those servers and discover stuff in them, study that stuff, characterize it, and then publish it in Nature and other wonderful journals. Fritz actually, what it does, it integrates two major software components. One's called Kowalski, and that's the system that we've been using at Caltech for. We've been using it as a sync for the ZTF alerts and also all the light curves. And I'll talk a little bit more about it in a couple of slides. And on top of that sits SkyPortal, the initiative led by Berkeley. It's sort of a modern, it's a science portal built exactly for that purpose, to collaborate on stuff and characterize and follow up and so on. And Fritz really integrates those two pieces together and adds some additional functionality on top of those. A few words about the development process. So we have several, in our team, we have several very active members of the open source community, most prominently Stefan van der Walt. And so we're striving to really trying our best to follow the best, the community best practices. So all of the code lives on GitHub. It's all open source, fully open source. Anyone can contribute. So there are three kind of main repositories for that. The central sort of piece is the Fritz repository that integrates stuff that gets implemented either on the SkyPortal or on the Kowalski side, and with some extensions and additional stuff in there. So that's where most of the action happens. For project management, we're using Clubhouse. It's not actually open to the public due to some constraints, but those could probably be lifted. So we use it to track progress on multiple fronts, on like storyboard things and so on. But most, if not all of those, are mirrored as issues on either of those three repositories. Just to give you a list of what Fritz has to offer is its features. As I said already, it's fully open source, it's free to use, modify and distribute. Fritz comes with powerful alert stream enhancement and filtering capabilities. It's featuring a extendable and scalable design. Both the SkyPortal and the Kowalski backends are written in async Python using async Python frameworks, and SkyPortal is using a React front end with Redux to manage app state. Comes with a very rich APIs for machine usage. So essentially, I would state that Fritz is an API first system, just like its components. It has fine-grained access control. You can authenticate using OAuth. Gives you a real-time Slack-like messaging experience with notifications and stuff. Rich visualization capabilities. Follow-up management for both classical follow-up facilities and robotic facilities that you can easily extend as well. You can do distributed computation using Dask. And for deployment, we support orchestrating with Docker Compose and Kubernetes. It's all well tested. Any new feature goes through the review process. Any pull request, any PR needs to get 2 green marks from 2 other people, and yeah, the CI should be happy, and so on and so forth. So let me focus a little bit on the first component of Fritz, which is Kowalski, and it serves as sort of a broker for alerts. As I mentioned, we've been using it as a sync for the full ZTF alert stream, but also for all sorts of other stuff as well. Most prominently, all the ZTF light curves. In addition to that, we have at this point over 30, I guess, external catalogs. Kowalski runs ML models, and it cross-matches the incoming ZTF alert against those external catalogs as they come in. For deployment, we have several beefy machines at Caltech, which come with like 50 terabyte SSDs and 1 terabyte of RAM. So we've been heavily relying on those. Just a couple of words about the technical details. As mentioned, it's built using an synchronous Python web framework, AO HTTP. And for the database, we're using MongoDB. There's a long list of reasons why we like it very much. If folks are interested, I can come back to this and explain a bit more. Obviously, all containerized, orchestrated with Docker Compose, can be deployed behind traffic IO for reverse proxy and load balancing. Just a few stats, like on the right side, this is how an alert is represented in the database. As mentioned, it's 30 plus databases, all the usual suspects. Currently, we have something like over 70 active daily users, and a typical load is hundreds of millions of queries per day. There are all sorts of activities that are supported by that service. Yeah, I'm actually saying tens of millions of queries. I checked it on the next slide, but I checked it last night, so it's looking more like hundreds of millions these days. To access the most in-demand stuff, we're indexing a whole bunch of things, and that take something like 5% of the total DB size. We're plugged directly into the IPAC Kafka alert streams, and to date, there are over 300 million ZTF alerts in there, and over 3.5 billion individual light curves. I would refer you to the open API specs of Kowalski's APIs that live over here. And we also provide a Python client to talk to the backend and to use the most frequently used API endpoint, so to say, so like you would construct a query something in a way like this, like I'm showing here at the bottom. As a part of Fritz, Kowalski allows people to filter the incoming alert streams. So people would define their filters, and Kowalski will run them on everything that comes in every night. So first of all, as I mentioned, it enhances the incoming alerts by first cross-matching those against the external catalogs. Then we run multiple machine learning models on the alerts. And those freshly ingested enhanced alerts with all like the full photometry history are then passed through those user-defined filters and posted to the SkyPortal backend, front end, I'm sorry. And those filters are implemented as MongoDB aggregation pipelines, and we've written very extensive documentation on how to implement, debug, and test those. And I actually have a screen capture over here. So what we did as part of the project is we put together several public databases for filter design and debugging with very extensive docs, again, as I said. So this is what I'm showing here. Namely here, we're using a tool provided by MongoDB, which is called Compass, to interactively design and debug a filter. So the cool thing about that, so you would see all the alerts as how they look like in the database, and then you would see exactly what each stage of your filtering pipeline does to the alerts, all the computations that it's doing, everything that passes and that is not passing, all the annotations that you're adding, and so on and so forth. So the idea is that people test out their stuff, and we provide guidelines on how to convert whatever people have been using previously to this language. and then you essentially just go ahead and plug it into Fritz, and the same night you see stuff coming in. On to SkyPortal side of things now. So SkyPortal has been envisioned as a data portal, and in big part it's been inspired by the PTF/growth Marshals. And it's also utilizing secure modern web technologies and can scale efficiently because of that, and is very highly customizable and extensible. A few words about its architecture. Again, the same modular design is employed. Let me just skip over here. So it sits behind an Nginx server that's used for load balancing, routing, and caching. On the back end, it's also using a synchronous Python web framework, Tornado in this case, and the communication between different parts of the SkyPortal is happens through WebSockets, which so for instance, coming onto front end. So here we're using React to display stuff to the users, and Redux to manage the app state, dispatch actions that would grab stuff from the back end, change the app state, and then re-render the components on the front end. Again, very extensive documentation. API. I will again refer you to the API, open API specs that are available on this link. And essentially all of the communication with SkyPortal can be done through the API. And to kind of finish on this, just several miscellaneous things about Fritz. So what Fritz does, it essentially mates Kowalski and SkyPortal, makes sure that they have tokens to talk to each other. They know where things live and so on and so forth. And on top of that, Fritz adds several ZTF specific API endpoints and front-end components, some of which I will show in screen captures in a few slides from now. For deployments at the moment, we actually have 3 live deployments of Fritz. One, a local one that runs at Caltech, and it's orchestrated with Docker Compose, and we've been using it with a very friendly army of beta testers, which we're very thankful for. They've been providing huge amounts of very high quality feedback, let me put it this way. Then we have a staging server running on the cloud on the Google Cloud Platform, to be more precise. That's orchestrated with Kubernetes, and for production, we're actually using a hybrid scheme where the SkyPortal side is deployed on the GCP, and the Kowalski side lives on those beefy machines at Caltech that I mentioned at the beginning of the talk. So it's orchestrated with both Docker Compose and Kubernetes. And yeah, we have a CI/CD pipeline in place for managing that in an automated way. And just one remark that our current focus is on transient science. So we're making sure that we have all the machinery in place for the transient science case, but we're pretty much done with all that. So we'll be shifting our focus on the variable and solar system science cases soon. So let me show you several examples of how things look like in practice. I'm going to show screen captures of how things look like in the browser, because I figured that it's pretty boring to be showing people how to issue REST API calls. But just to reiterate once again, it's an API first system, so everything that you see happening there happens through the API calls. So this is just this is just a demonstration that we have access to all the alerts ever issued by ZDF. So you can look up all of them, look what the thumbnails were for any of those, look at all the cross matches with all those catalogs. If you like the source, you can go ahead and save it to your program, rather group or science program, and then go to the source page, type in that you like this source very much. That's how it all looks. Here we're using Bokeh for rendering the photometry, and Vega Lite for rendering and visualizing other stuff like the offset plots. Like, I liked it so much that I assigned this target to an observing run. We'll look at that in a moment as well. Then just a demonstration. I mentioned that where we have pretty tight integration with the follow-up facilities, and both classical, so to say, run in a manual way, and robotic. And in this case, I'm just showing an example of an SEDM spectrum that was requested and then observed, and then automatically posted back to Fritz in here. Another screen capture. So I am just showing how to add a filter and then save it, and what it would look like. So like you would select the stream that this filter would operate on. You save this previously debugged MongoDB pipeline. We have tools for handling versioning of those filters, so you can look at what the diffs look like between the different versions that have been in production. So you see how you saved the filter, and then the same night you would go to the scanning page and look at the candidates that passed your filter. So that's what the scanning page looks like. You would scroll through, you would see something that you like, then you would save it to one of your groups. Say I want to save it to my group, and go there. And yeah, essentially the same as we've seen before. Now I'm pretty sure it's a transient, so I would go ahead and add a classification for that. Or actually I changed my mind and thought that it's some sort of an asteroid or something. And yeah, I'll try and generate the finding chart. I'll see. I think it'll show up eventually. And while it's being generated, so you see there are all sorts of components, so rendered in here. So all those things are easily extensible and can be added as needed. Let's see. And yeah, just to reiterate once again, let's see, I think I had another, yeah, I'm sorry. So I had another slide just to show how the allocations work with sort of classical follow-up facilities. So all sorts of things are displayed on this page. You can generate star lists for whatever facility you're using, and change the state of those targets that you have in your list. And just to reiterate once again, all of the actions that I've just shown, they can be carried out programmatically using the API, and that's actually what's happening on the front end. So the Redux would make sure to issue the dispatch, rather API calls, fetch the stuff from the backend, and then render or re-render the React components. That's it for me. So I'll be happy to take your questions, and thanks a lot for your attention.
Well, thanks very much, Dima. If people would like to, I certainly have plenty of questions, but if people would raise their hand, and then I can call on to ask you questions. So I see Chen Hugh. Sorry, I've massacred your name there. Oh, you're clapping rather than raising your hand. Okay. Well, while people think of, my apologies. While people think of questions, I had one actually. I might ask about MongoDB later if there's time, but in the SkyPortal diagram, I had two questions actually. What Python framework are you using for the web front end? And the other one was, what does the Postgres DB actually do in SkyPortal? Because given that MongoDB is your main sort of data database.
Yeah, so let me clarify that a little bit. So Kowalski's database and SkyPortal's database, they're completely separate. So
yeah, I assumed that.
Yeah, so Kowalski handles storing those external catalogs and serving as a sink for the ZTF alerts and light curves. So that's one thing. And then the SkyPortal, it's using only Postgres, and all of its interaction with Kowalski, all that as part of Fritz, happens via API calls. So all of the stuff that it stores in the Postgres database.
Okay, and another question. So Tornado, is that a Python web framework? I'm just not familiar with it. That's all.
Yeah. It's I would say it's a battle-tested asynchronous web framework. One of the first ones that came out, and it's been pretty active for the past, I'd say, 10 years or something.
Okay, cool. And so this is very impressive. Even not considering the sheer volume of data people can access and the rate at which it increases, it's very impressive just in terms of the functionality you have, and then that it's working on top of such a huge pile of rapidly accumulating data is particularly impressive. I see David Kaplan has a question.
Yeah, thanks a lot, Dima. Maybe could you address questions about data privacy and the different, observing groups and multiple parallel projects and follow-up groups and things like that?
Yeah, sure. So I think I had, so in the list of features, I mentioned that we actually have fine-grained access control. So we're using ACLs, and we have a long list of available ACLs, which can be grouped into user roles. And so that's one part. Then as far as data access control is concerned, so we are distinguishing the source of where the data came from. So those groups that I showed, anyone can create a group, but only a set of system admins that have enough ACLs to do that kind of stuff can assign data stream access to those groups. And those kind of those are defined in the config and at the moment. So we're only supporting ZTF, but this can be extended to whatever else is there. And those groups can only see stuff that comes from the corresponding alert streams. And people can very precisely define who can see what. For example, by default, if you're uploading data, that data would belong to you only, and that's implemented via single user groups, similar to how it's done in Unix, if you're curious about the technical side of things. And then you're free to share it with whoever you want. So just to say it once again, the access control is very, very fine-grained and can be, so you can be both as restrictive or as open as you like, without worrying about people accessing data that they should not be allowed to access, or the other way around. If you want to be fully open, you can do that as well.
Okay, cool. I see Andy Howell has a question.
Yeah, if I downloaded and spun up my own instance, what databases would come with it? I mean, you mentioned there's like 10 terabytes of database stuff somewhere. Does this thing point to those,
Yeah,
or do
so
you have to
that
start your own?
you would for that you would actually at this point you would have to ask me, because that stuff lives on the GCP, and like egressing 10 terabytes of data is a little bit expensive, which we haven't figured out like very robust way of handling that, but we can sure come up with something eventually. So yeah, we provide dumps of those databases that can be loaded into Kowalski for cross-matching purposes. Then again, since you mentioned that when you are so when you're spinning up your own instance of Fritz, you would need to point it at an alert stream. So there should be a Kafka stream somewhere where you would grab things from ZTF alerts, namely, and put them into the database.
Thank you. And yeah, nice work. It's very impressive.
Thank you.
Cool. David has another question.
Yeah, so maybe also sort of going along the lines of what Andy was asking. So ZTF does have a public survey. It is generating public alerts. Do you think that, for somebody who's not part of the ZTF collaboration, if they want to build on Fritz or use it, is the right way to think about it that they should start up their own instance like Andy was suggesting? Or is there a model where, your group will support, a purely public access stream?
Yes,
And
that's a
then
great question. Thank you.
A sort of related question is, in a few years, if LSST VRO alerts start coming through, are you going to be able to handle them? Can you just plug into that stream? Are there scalability questions there?
Right. Yeah. Thank you. So as far as the public-facing stuff, so first of all, as I said many times, it's open source and anyone can spin it up whenever they want. That's one thing. The second thing is we're definitely thinking about making a public-facing instance of Fritz that would be available to essentially everyone, and that would serve the public data that ZTF provides. It's a little bit too early to be more specific in this respect, but this is certainly something that we're contemplating and thinking about. It's just that we, with the phase two kicked off 5 days ago, so it's been our main focus so far, and we started this project in late February. that's where we had the first meeting. So it's been a bit over 6 months essentially.
No, there's a comment in the chat as well, just that there are several public alert brokers that are already streaming sort of ZTF public alerts, so like Alertons and Antares and Lazea. So I guess, as a member of the public who's not in ZTF, you can already currently get your aggregation of and filtering of ZTF alerts.
Mm-hmm. Yeah. But they do provide access to filtered. So are there brokers that provide access to unfiltered public alert streams that anyone can plug in? Does anyone know?
I think Gautam may have an answer.
Yeah, I think actually all of the brokers will let you have access to the unfiltered public stream if you want to. All of these alerts that are saved in Lacer, in Alersi, and Antares can be accessed either through an API or through their web interfaces, and so you can apply any other filtering you want downstream from them. And the plan is to do this for LSST as well, so that the brokers are effectively acting as rebroadcasting the stream from LSST itself. And this is partially because LSST had initially some questions about bandwidth. Now, I don't know if Mario's on, but then there may be new developments to sort of ease that in the future. But the idea still exists, and I think we still have the capacity to do that.
I see. Thanks, Gautam.
Yeah, Mario is not on.
I think I
Unfortunately.
saw him
Oh,
at some point, but
yeah, he may have dropped off. So, and in fact, we will be hearing. We're going to be having another public telecon next Tuesday, where we'll be hearing about brokers from Gautam and probably others. So, one thing I wanted to ask actually.
I'm sorry.
Go ahead.
There was a second question from David on.
Oh yeah.
Will we be able to handle LSST? Well, definitely, but especially SkyPortal was built with LSST in mind. Eventually, with the first focus being ZTF. So it essentially turns into a question of data store. Like, do you want to store everything, or you just store the filtered stuff and so on? Because ZTF with the current deployment schemes we have, we can easily handle ZTF when the data volumes become 10x, 100x, whatever. Yeah, we need to think about that at this point, but it's definitely doable.
So I was going to follow up. So I was just quickly looking at the Dask webpage, which seems pretty cool. So two questions related to scaling, really. So is all of this running in cloud, so that you grab stuff from IPAC and then everything's in cloud? And then exactly what distributed computation are you doing with Dask?
So Dask lives on the SkyPortal side, so it's whatever you want to compute on the stuff that has been saved to SkyPortal, that passed your filter and for example was saved to the science program that you're part of. So then you can do that's where Dask is being used for
Okay, but I guess the thing, have you spun all this up in, say, Amazon or something like that, and dealt with all of the well, not difficulties, but all of the issues in terms of like controlling your spend and so on, or are you running this on-prem?
No, so the production version, it lives in Google Cloud, on Google Cloud, and yeah, that we're dealing with all this DevOps stuff. Yeah, so do you have any more specific questions in that regard?
I can imagine us coming up with some as we move on. We're currently deploying our stuff in AWS and trying to feel our way. But I think at some point we will be interested to hear from people who have spun up in other public clouds. Now I do actually have a couple more questions, but I'd like to hear from someone else. Okay, Rich Kowalski has a question for you.
Oh yeah, maybe I can follow up on Adam's question. So we're looking at things like, how do we produce an audit trail? We've got a DevOps team. DevOps team is spinning things up, spinning things down. It's generating cost events. We have a monitor that's posting to Slack daily what the spend is. What we're working on is, okay, if we've found that something's runaway, how do we trace it back to its origin? Do you guys have auditing facilities, logging facilities, monitoring facilities within this that crosses your services and then also cuts across the resources within GCP so that you can figure out, root cause basically for an overspend or a failure or an ACL depriv, something like that?
Yeah, so we're using Papertrail for monitoring the logs, but currently we don't really do any tracing on like overspending, as you say, because essentially what lives in the cloud is like several Kubernetes pods, which are pretty moderate in their size, and the only place where I could see where overspending might happen would be data egress. So if someone requests a whole bunch of data from Kowalski, but that's kind of easily traceable, and essentially the only way to deal with it is to do rate limiting, like the amount, either the number of API calls that any one user can issue, or the amount of data that they are allowed to get. But at this point, we don't really want to limit specifically our internal ZTF collaboration users in that respect. So yeah, but thanks for bringing this up. But otherwise, I'm sorry, just finishing off real quick. It's very cheap to run this whole thing in the cloud, provided that no one tries to download all the full ZTF alert archive. Then the cost would be the data egress.
Okay, yeah, that's good to hear. I see Vlad has his hand. He may have a similar sort of question or follow on.
Actually, as a small follow-up to the previous question, so as you can tell, our main concerns are overspend because of a mistaken intrusion, or some kind of intrusion through one of the many credentials that we have and we afraid might get leaked. So I was curious, what are the main security concerns that have been considered in your project?
The main security concerns. So we are, as I mentioned, so essentially the only, there are very few things that are exposed to the outside world, and the ones that are, you can only get access to them using the tokens generated on the back end. And there is a slight chance that those tokens might leak from someone, but then again, it's a tough question, because there are very few points where something bad may happen. And but do you have any specific security concerns in mind that you want me to comment on?
Well, I just brought up these two because that's what we think about a lot, and we've been talking about that and getting consulted on it. So I just want to see a perspective from some other project. So that's it, but thank you.
I see Rich has his hand up again.
Yeah, maybe I can follow up on that. So we are concerned about things like intrusion detection. So, if we have several collaborating services running in VMs, let's say, and one of the VMs is compromised, either through an SSH attack or some other problem, and we've given some thought to how do you cauterize that? How do you shut down the compromised resources, having determined that they're compromised, while not necessarily shutting down the whole service? And also we're struggling with, the notion that the team that's working on this might itself be transient. So rather than having 4 developers full-time for 2 years or something of that nature, what we're finding is that we're getting a piece of developers on, say, a 6-month cycle. And so there's a credential turnover in the DevOps team that has spend authority, right? These people can generate spend events. And some of these things can be surprising. You spin up something in a service, maybe with a third-party piece of software, and suddenly there's a $10 or $12 a day expenditure that you didn't anticipate, which isn't not any great deal, a big deal if you find it quickly, but can easily accumulate over time. And that's just because we have a bunch of developers who are sort of spinning in and spinning out of the project, and they're trying different things, different services that might be useful. So we're trying to do this tracking and monitoring to ensure that if there's a security event, we can detect it quickly and remediate it quickly, and then B, to try to manage turnover in the DevOps team, we're trying to use the same mechanisms.
I see. Thanks for the clarification. So let me comment on this. We actually have, well, we don't really have a DevOps team, so we all do a little bit of everything, and we have a very limited amount of people who actually have access to the to GCP, and so it's pretty easy to see what's happening where. And yeah, so that if that's what you're talking about, I thought maybe like how would someone would get into the system using, like, I don't know. Yeah, that's why I said we're not exposing anything, so you cannot just SSH into those VMs on the outside world.
Let me just follow up real quick. So if one of those small number of people were to be compromised, though, do you have a remediation plan, an action plan? Someone's SSH keys get stolen or a laptop gets stolen or something of that nature, of that small team for GCP. You know, have you thought about how you would detect that and then remediate the system or protect the system against that stolen credential?
Yeah, we haven't gone that far. No, we just essentially,
Thanks.
as I said, couple people spinning stuff up on GCP, and that's it essentially. And we're just looking at whatever's being spent, and those the amount of resources we spend is really low. So we've been kind of monitoring it in a manual way, so to say.
Okay. Question from David?
Yeah, so you mentioned that you basically started this all in February and you are live as of last week, correct?
Yeah, that's right.
So you know, obviously you had to make a bunch of decisions early on in terms of platforms and methods and things like that. Did you make the right ones? Are there, you know, broader lessons in terms of specific, you know, development techniques or platform choices that you would remake, or are you pretty happy with where things have ended up?
I can confidently say that I'm very happy about the choices that we've made, and they've proven to be the right ones, at least for our team. I can comment more on like specific parts of those if you're interested in hearing that, something more specific.
I was wondering, because you're a distributed team, how you did you sort of day-to-day or week-to-week management of software development?
So we have a weekly 1-hour Clubhouse sync meeting where we do iterations for 2 weeks. We write storyboard things, assign them to different folks. Those get accumulated in epics, and those epics, like parts of them get assigned to different iterations. So that's how we track progress. Those things, so that all happens in Clubhouse, and individual parts of those stories get linked to issues and PRs on GitHub. So it's kind of a day-to-day thing. And then also for the past couple months, we've been doing a daily stand-up at 9:45 for 15 minutes, where people give very brief updates on what they've been up to, what kind of stuff they've been working on since yesterday, and whether they're blocked on anything. And that's been a huge success. That's actually coming back to David's question. I would, if I could start over, that's the thing I would immediately do. that would be the number one thing, because if you just look at the graphs on like how much stuff has been contributed to SkyPortal and Fritz and Kowalski in the past couple of months, you would see huge spikes, and that's when we adopted this daily stand-up thing to sync on things. That's been hugely successful, and I would urge everyone, if you can, to do the same.
Yeah, that sounds broadly similar to the approach we've taken, and for the same sort of reasons. So we're nearing the end. Does anyone have another question? I do have one question, but I could address it by email if someone else had one. Okay, so you did promise earlier on you could do a quick run through of why MongoDB. I'm just interested because I'm a database person and we're moving towards deciding about databases probably for production, rather than just prototyping. And I wonder what your reasoning was.
Yeah, so the reasoning here is that, well, first of all, I just kind of like it. But the technical reasons are that we felt that NoSQL maps very naturally to the structure of the alerts. So the Avro format used in ZTF alerts essentially directly translates into a BSON that's used internally in MongoDB. And then we essentially don't have to worry about the evolving schema. So in ZTF, we're now on version 3.3 or something. And there's actually very little logic that needs to be taken care of downstream. But on the database side, there's no downtime for like migrating the schema and stuff like that. So it's super flexible in that respect. Then as far as storing the light curves, and a huge benefit that we've seen is in the way things get stored. So if you need to extract a whole bunch of data points per source, you would do essentially one read as opposed to like reading of multiple rows. We've just had a paper out. Well, it's out on archive. It's one of the papers on the ZTF source classification projects where we actually show some performance graphs on on that. So I would urge you to take a look at that. It's called ZTF Source Classification Project 2, and first author is Michael Coughlin. So where we basically show like what's the latency depending on how many light curves you want to grab at once, and so on and so forth. So we've been very happy with the performance that this thing provides. So that's one. Then two, we really like that MongoDB has built-in GeoJSON support with 2 indices on the sphere. So things like current searches are kind of supported out of the box, super fast and optimized. And it's even better is that the MongoDB team is super responsive. We've been talking to them. We've been telling them what we would actually like to see on the data, like at the database level, and they've been very responsive. And they're actually working on some of the stuff that we requested that is very appropriate to to astronomy use cases. So there's a lot there already, and even more is coming. Then the query language. So we really like these aggregation pipelines, and this screen capture that I showed on how to interactively sort of play around with whatever's in the database and see what would come out of your filter kind of live. It's a very powerful tool, and they're expanding it even further. So you can do a whole bunch of different computational things as part of those aggregation pipelines, and they've recently added the ability to run just custom functions as part of that. They're only supporting JavaScript definitions at the moment, but they have a keyword for language, so I presume that with more stuff would follow soon. So you don't have to worry about security if you allow your users to use Python functions, for example, and so on. All that stuff would happen, and the database would take care of that. And finally, horizontal scale out of the box. You do need to worry a little bit about how you shard your data, what you do with the shard keys and so on and so forth. but there's not really that much that you need to worry about. So that really comes back to the question of whether can we support LSST at full scale? Yeah, just horizontally scale out. So it just becomes a question of how much you pay for like storing things, and that's essentially it.
Oh, great! You seem to have got the whole grab bag of benefits that MongoDB offers and actually applied them. So we're at the hour.
I'm not like a MongoDB salesperson or anything. It's just that in this particular case, I honestly think that the benefits overweight whatever may come with a SQL database.
Yeah, I'm inclined to agree. I think, and we'll have similar decisions to make for ourselves. So we're on the hour. I'd like to thank you for a really interesting talk, and this will be available on YouTube for people to look back if they have more questions to come up. And it's like thanks very much for coming and talking to us. And next week we'll actually be hearing about brokers, which is sort of relevant and aligned.